Great. Well, thank you very much. Thank you for still being here. And okay, I should get that one too. Yeah, I do theory. And Marcos, thanks a lot for inviting me and Hossein. It's really a fun workshop. Also, thanks to John from my side for the whiskey yesterday. That helped making the slides. So I'm actually, I'm not sure myself what's coming. So it's going to be interesting.
Did you change the title afterwards?
No, the title stayed the same. Okay, so here I just wanted to give you a little overview of the type of research questions I've been working on. It's a continuous collaboration I've had, and there's a lot of different things we explored, both down-to-earth things in terms of experiments and a little bit more conceptual subjects. So I'll try to just give you a brief overview of that, where we studied the role of proper time in the context of superposition states, matter wave interferometry, or even more kind of crazier ideas. Okay, so first let me start with advertising that we have positions, PhD and postdoc positions in theory. And so we're excited to do lab cosmology without having any lab, but just thinking about it. So if you know of anybody that is kind of interested in this field or all types of subjects that fall into it and want to do theory, please let them know. So the outline of my talk is first I want to talk actually about cosmology. So somebody pointed out, I think Shimon pointed out to me that this workshop has not a single talk on cosmology. And so there's a small interlude just on one project that I did that related to cosmology. So that's just going to be a few minutes and has nothing to do with the rest of the talk. And then I'll talk about this superpositions of proper time and how that first relates to some Gedanken experiments. It's some most recent result that we had from a few weeks ago, published from a few weeks ago. And there I'll just show you how you can talk about Bell's inequality for causality and what that implies for quantum gravity in general. And then in terms of laboratory experiments, I'll just talk, second half of my talk about new effects that appear if you include post-Newtonian corrections to the dynamics of matter wave systems. And in particular, we'll focus on time dilation and what type of experimental signatures there appear. And then finally, if there's a little time, just to briefly mention that also leads conceptually to a decoherence of a composite system in Earth's gravitational field. Okay, so this is just a little kind of outline of different subjects that I find interesting. And that is on this interface between AMO physics and low-energy physics and fundamental physics. And there's different aspects of it. So there are simulators and analog systems. And I think Rivka Beckenstein was the representative of that, at least her previous work, this workshop. Of course, high-precision measurement, leveraging all kind of possibilities that we have of AMO systems. But then there's also more conceptual and kind of theoretical ideas inspired by low-energy quantum physics, and that we know. So one is, quantum effects in cosmology. Also inspired ideas of entanglement and just quantum information context to better understand nature of space-time. And then this is kind of my favorite part here is studying possible effects of quantum gravity or some models of quantum gravity, speculative things, and what kind of experiments we could make. And then also about known physics, but in a regime where we haven't probed them yet, in particular quantum theory on a curved space-time background. Okay. So first, let me say just a few words about possible quantum phenomena in cosmology. So yeah, since I'm the only talk on cosmology, here's just kind of a two-slide overview of kind of a very basics of this entire field. So the idea in cosmology is that most likely there was an inflationary period very early on in the universe that was suggested in the 80s. And what it implies is there's a very rapid expansion, which is nice because it homogenizes the whole universe. And you get a mostly flat one. So this is something we observe today to the most part. And so this is described relatively simply by this specific metric, which is the solution to Einstein's equation, with one free parameter, and this is A of t. And so this A of t is what governs how much the spatial distances are actually expanding. So the models of inflation are those that give you this expansion, which grows exponentially for a certain period of time. So you have to solve Einstein's equations to find out what A of t is, given the matter distribution, and that gives you this exponential rise. So this is captured often by this Hubble parameter h, which is just A dot over A. Okay, so if you go through the Einstein equations and you assume just a very simple matter model, which is just one scalar field initially, then you get very simple equations of motion which are coupled to each other. One for this h, so effectively for this a of t parameter, which scales the universe, which is a function of this field. And the other is the equation of motions for this homogeneous field, assumed just by by construction, which looks like just some kind of damped system. So now it depends on what you postulate for this initial potential for this scalar field to be. So this is just something that's put in the model. Okay, so this is like a damped, slow-rolling particle solving these equations in some specific potential well. So if you can choose some kind of potential where initially, it some kind of has a lot of energy, then you get a lot of expansion, and then after a while, this field has actually very low potential energy and low kinetic energy, and so then the expansion stops. So this is kind of the basic idea of this inflation models. Okay, and then on top of that, you can assume some kind of inhomogeneities. You can even quantize them, and this is something that you actually see on the CMB as well. So that's a nice way to explain many of the features that we see today. Okay, so now one example that people have studied is a potential which actually is some kind of tilted potential. So that's one proposal that was by Abbott given in 1985. So you have this kind of periodicity, and then you have also this tilt. So in principle, if you had just some kind of classical field, it will be stuck somewhere if it doesn't have much momentum. And then if you add quantum mechanics on it, then it can tunnel down this potential well, and so you get this kind of slow decay such that inflation stops at some point. Okay. But in principle, if you take quantum mechanics seriously, it's not just simply tunneling that you can have. And so this is where kind of this AMO inspiration comes from. In principle, there's nothing that forbids you to have quantum states of the homogeneous field, which are also superposition states of possible kind of classically allowed values. Of course, if there's no decoherence, but this is all just some models. Okay, so if you have this kind of classical quantum superposition state that's allowed, then we also know what happens from low energies, and in particular these are Bloch oscillations and this kind of potential. So this is something very different from tunneling. This is not a perturbative kind of effect, but this is really the full quantum dynamics of the system, which is completely different from the intuitive classical picture. And so this is something that then would happen depending on what your initial state of your initial homogeneous field is. It would kind of delocalize over many of these potential wells and then recohere as well, depending on, maybe initially it was spread out, then as a whole, as a whole Gaussian packet, it would oscillate back and forth and not simply roll down the potential well. But then if you add also, this damping term, then it will actually slowly decay as well and, decay these oscillations and go down the potential. So in principle, if you had some kind of quantum coherence like that, you have some kind of other phenomenology in, that might have taken place in cosmology, and you get also an observable signature of that on the CMB, which is some oscillations on the power density spectrum. Okay, so this was just a small interlude of a paper that I did here at the CFA, where... Yeah.
Sorry, quick question here. So,
sure.
I'm sure you made then some estimates on the strength of these oscillations.
Yes and no.
Okay.
Yeah, well, to be really honest, you can't really make estimates of how strong they are, because now you need to assume, now you're going kind of from a quantum superposition state of the entire universe or the inflaton field to something that connects to some kind of experiment. So you do some kind of mean field, approximation to that. Basically, what you just say is you bound it. So you don't see oscillations, then, it means that, you didn't have anything of that sort. So you don't have exact numbers or something like that in there. But because you have so many free parameters in terms of even the initial state of the field, what potential we've been talking about, it's more about, the prediction would be you would see some small oscillations in the power density spectrum, and then, yeah.
So, because in this treatment, you're not putting the Hubble constant into superposition, you're just estimating the mean field?
Yeah, so here basically the effect would be, like, in the end, you look at some kind of maybe mean of this result. Otherwise, you really get into quantum gravity, and then, yeah. So here is some kind of phenomenology where I assume, okay, it took place for a while, and then as soon as kind of the modes decouple, maybe they kind of, only carry mean field information. Okay. Right. Well, so this was just a little interlude. It's kind of not so much lab in cosmology. It's more about, from lab coming here, seeing this beautiful Bloch oscillation experiments, inspiration towards some kind of, cosmological questions. And I think actually there could be many, many such things. Quantum effects that we know from quantum optics, quantum information theory, which are just simply not something people think of in that field. Okay. So now let me move on. It's still, still a little bit Gedanken experimenty, but here I want to talk about, maybe a somewhat less speculative physics, just exploring what kind of consequences we have if you apply concepts from quantum theory and gravity as we know them. Okay, so in particular, I'm going to talk about Bell's theorem, and Bell's theorem for temporal order. It's a very powerful technique in terms of specifying, without any underlying theory, in some kind of, in some sense, no-go theorems for how any underlying theory would look like. So in other words, it forbids any kind of classical, local, realistic notion of the underlying physics. So it basically just says that, explaining local experiments on both sides, Alice and Bob, in terms of, possible experimental settings they can do and all possible outcomes they can have, is not possible with just a probability distribution which would be governed in some kind of, classical deterministic world in terms of a hidden variable theory. Okay. So to do this Gedanken experiment, it's a little bit of doing relativistic engineering. So the idea is the following. We use time dilation, which just says that if you have a massive object and you place it nearby, some kind of clock, then it will slow down this clock. So if you have two events, say A and B, and then you place a Earth near one of these events, you will slow it down. So it will become, if they were initially time-like separated, and then you, space-like separated, and then you, you place, a massive object near one of these clocks, then it will be delayed compared to the other one, such as in the future light cone of the other one. If you place the mass on the other side, you can delay the other event as compared to the first system. So it's just to say that light cones are also dynamical depending on the mass distribution. So as the mass distribution changes, the light cone structure of space-time changes as well. So you can be either in the future or in the past of each other, depending on where you place a massive object. Okay, and now you go further than that, so you don't do just classical relativistic engineering, placing neutron stars in different places, but you also do that now quantum mechanically. So you have some beam splitter with a neutron star on Earth, and you place it in either of those two positions. And so what you create is a superposition of different causal orders, which you can have. So just schematically, if you have some kind of wave function that go from one to another, in the one case, first it passes A and then it passes B, and if A and B just imprint locally some kind of operation, they don't even need to know anything about the space-time structure. They just get some system and imprint a unitary on it. Then you get this kind of overall state. And in the other case, if it first passes B and then A, then you get a state which is different. So you swap the orders at which you apply operations. Okay, so you get an effective state, which is a big entangled state with your big mass, but which this order of operations is superposed. So there's some kind of superposition of these causal orders of specific operations. And so with that, you can formulate some kind of a classical, let's say, theorem if you cannot do any superposition of causalities. So if space-time is classical, or not just space-time, if kind of time causality can only be classical, you can formulate some, in the same way as you formulate in the other Bell theorem, you can assume four things. You have two space-like separated labs. You do only local quantum operations. You don't share initially any entanglement. So you have systems which are going one way or the other way. So these are these two labs, and these labs perform operations A and B on each side, and then they do some measurements, any arbitrary measurements. And so they get some state initially which has no entanglement, just a product state. And then from that, you can show that there's like a probability distribution which can never violate a Bell inequality. Okay. And so, if you do this kind of superposition state of some massive object, you can go, around it. In particular, so if you are here in this orange state, then on one side, on both sides, you apply first operation A and then operation B. if you are instead on this kind of blue configuration, then on both sides you first apply operation B and then you apply operation A. And again, we're talking here about a product state on both sides. And then, of course, in the end, you have to, again, remeasure the mass just to project it out because otherwise you're a big entangled state. Okay, so what you do here is that, again, you have space-like separation, you have locally quantum operations that you do, and you don't initially share any entanglement. So you kind of can make sure that this is all okay. And then the only thing that you violate is that you actually had this classical order of events or some kind of classical notion of causality. And so in this, in this kind of scenario, you get this kind of entanglement between temporal orders of events which are separated. So you have a superposition state, and one where on one side you apply first A, then B, and on the other side you apply first the B unitary and then the A unitary on this kind of product state. But because you now created an entangled state only by changing the causality, you actually can violate a Bell inequality. So, for example, if initially you have like a product state of two photons, and then you measure polarization, so you can just choose specific unitaries that they agree upon initially. Then, in the end of this protocol, you get some entangled state, Bell state, and it's easy to show. This is then the standard violation of Bell inequality you can do with just by doing standard measurements. So, in other words, if you start with a product state just by using space-time as a resource, or time, actually, only time, the causality, you can actually do some quantum tasks that you can't do classically. Okay, so what this just teaches us is we don't assume anything about quantum gravity. You don't need any kind of machinery or ideas from quantum gravity. Just by using very basic concepts for quantum theory, quantum optics, or quantum information theory, you get some kind of results which have to be valid for any theory of quantum gravity because it's a theory-independent result. So this causal structure inherits all these quantum properties that we know are strange in normal quantum physics, contextuality and lack of realism and so forth. So that has to be true about time and causality itself within any theory of quantum gravity. And also another thing is just there's all these models so that motivate some kind of collapse of the wave function to forbid some kind of superposition of causalities in some sense. And you can show that this specific protocol, no matter what type of system you take, you can always do it faster than any collapse time occurs. So in some sense, it kind of makes it void. The whole motivation of these models is to forbid these scenarios, but you can always find a time scale at which you still can violate this Bell inequality before it has collapsed. All right. Okay. So now let me move a little bit away from Gedanken experiments, more down-to-earth things. So this was a science fiction scenario, and I think the main motivation for me to talk about it was, I think it was the pinnacle of my scientific achievement in my lifetime, because for some reason Fox News thought it was interesting. And the reason for that is because we tried, I think, to explain this in terms of starships, some kind of science fiction scenario where you have two starships that are shooting each other, and you're in superposition of both being destroyed and surviving. So you can actually cook up very interesting science fiction scenario in these cases. But a bit more practically, in a very similar way, we can actually talk about experiments on Earth, just lacking one ingredient, which is the superposition of space-time. But there's still many interesting effects that appear. So we can do something similar, talking about time dilation and time and superposition states, but that the classical background space-time is just fixed. So it's just classical, and there's no notion of quantum gravity there. Okay. So this is going to be now the second part of the talk, maybe more exciting for the experimentalists. So this is about quantum dynamics and curved spacetime and what implication it has for matter wave interference experiments. Okay. So we heard it already a few times here that there have been experiments already that do probe the gravitational influence on the dynamics of quantum systems. And the canonical example is the COW experiment, where you could see a phase shift in a matter wave experiment induced by Newtonian gravity. So this is just governed by having a Hamiltonian, which also has a potential, which is the gravitational Newton's gravitational potential. Effectively, in this kind of interferometer, the state of your probe particles in a superposition of two different paths with a relative phase, which is induced by this gravitational potential. So this is actual data that they observed. So as you look at the probabilities of detection in both of these detectors, you see these oscillations, which is exactly the phase shift induced by gravity. So as you rotate the setup, you change this phase shift and you scan this phase. So this was first done, like I said, 40 years ago or soon 50 years ago in this kind of small setup. And this is also at the heart of today's atom interferometer experiments, where you see this kind of gravity-induced phase shift, like in Mark's group, up to 0.5 meter separation scale. Okay. So what we learned from these experiments, just conceptually, is that we can add gravity into our description of the quantum dynamics, just as we would add any other force. So it affects the gravitational wave function, the wave function, in the same way as, for example, electric potential would. And it's a coherent effect. So what we don't learn anything about it is if we go beyond Newtonian physics. So, and I think this is kind of a main point. So gravity is not a force. So it has, many other things and many effects that take place, which are conceptually different, and we don't see in electromagnetism. So going beyond just simply a force description is by itself interesting because it probes the metric nature of gravity and how that changes the dynamics of quantum systems. And of course, also these type of experiments don't learn anything about the quantization of gravity. So what I'll talk about here is just how time dilation affects these type of matter wave experiments. So this is going beyond the Newtonian description in a very specific way, looking only at a very specific kind of physical effect which takes place. So we all know that time dilation, of course, has been measured in many of these experiments, and we heard it in many talks already. So if you have two clocks and we put it at two different heights, they will measure different proper times. And so this has been, and the clocks can, of course, be quantum mechanical, and in fact, they are quantum mechanical. So we use atomic clocks, meaning we use atoms which coherently evolve, so their atomic wave function evolves with respect to some local Hamiltonian, but it also evolves with respect to the local proper time. So this is just to say that anything that we ever measure always is just the proper time of the system. So we know, in other words, already from all experiments performed today, that in the Schrödinger equation we have to include proper time and not coordinate time. So this demonstrated with cesium clocks also many years ago for the first time, and then very nice experiment that Shimon mentioned is this 1 foot separation where you can see the time dilation between two ion clocks at 30 centimeter scales. Okay, so that we know, and so just to clarify, we do know that quantum mechanics works and measures proper time in the same way as we would expect. But what is not tested is that this quantum system itself is delocalized over an extension of space-time where you have to take GR effects into account. So in other words, that is quantum theory on a curved space-time, which includes post-Newtonian corrections. So everything here is always like localized. The position is localized, but the internal mechanism is quantum mechanical. Okay, so what we looked at is if the clock itself is delocalized of a region of space, which is beyond kind of the Newtonian approximation. And to describe the effect is extremely simple. The only thing you do is, again, just you use linearity. So like I said, we know that if a clock is on the lower path, it ticks with tau 1. If it's on the higher path, it ticks with tau 2. By linearity, we know that we can just add those two results together such that we can create a clock ticking either at tau 1 or a clock ticking either at tau 2 in superposition. So in particular, if you have some kind of, say, atom that you split, a matter wave that you split, but it also has an internal clock mechanism, then you get an effective wave function as before, where it goes either on the lower path or on the higher path. You have some relative phase between them that you would see on this path interference, but on top of that, you have an entangled state with the internal clock states. So this is the novelty and the difference to any other description if you just have a force description of a system. Here you have a conceptual new effect which entangles different degrees of freedom, which are only entangled by the presence of a GR effect. So the clock ticks at a specific rate on the lower path and at a different rate on the higher path. So if you just want, for example, to do just interference, like you do in atomic fountains, then you trace out these clock states, so you don't even look at them, you just integrate them out. But because they tick at different rates, the overlap of those two is what gives you which way information about this kind of interference experiment. And so you can derive your overall visibility of your interference due to this availability of which way information in the clock state. And so this is a generic formula, very simple to derive, and it depends on this internal clock Hamiltonian and the difference of proper times along these two paths. And it's generic because time dilation is universal. So any Hamiltonian, it doesn't matter what type of clock you use, so this H0 is just a Hamiltonian for your clock, it will give you exactly always the same result here. So just as an example, let's say you have a two-level system, so you have an atom, so you initialize it in superposition of, I don't know, hyperfine states or something like that, and then on top of that, you do spatial superposition of these systems in an atomic fountain. So you have like in some sense, a nested interferometer. So you have an interferometer of the internal states where you create a superposition, and then you split it in two different paths to go spatially at a higher or lower path. So this would be like this kind of two-level system, and the prediction here, if you include GR, is that not only do you get a phase shift, so you get effects on the phase shift as well, and maybe you get GR corrections or whatever corrections on the phase shift too, but you get conceptually a new effect, which is this change of your overall interference visibility. And so this change in interference visibility for a two-level system is also a periodic function. It's a absolute value of a cosine, which depends on the frequency of the internal clocks as compared to basically the proper time difference between these two paths. So without a clock, you would just have this phase shift. This is this black line, and then if you have the clock, then you get this blue line. It's a little bit shifted, but on top of that, it's modulated with an additional function. So it's this modulation, which is a signature of quantum physics in the presence of some kind of metric effect, which goes beyond just simply a force or even a modification of the force. Because any modification of the force will just shift your phase back and forth. Okay, so this is just kind of the message I wanted to drive home. So if you have a phase shift and you observe that, and this is usually what microwave experiments do, then in gravity it's just Newtonian potential with absolute time. It's always analogous to any kind of Aharonov-Bohm effect or any kind of electromagnetic effect that you can have. And you don't need the notion of redshift. So even if you take some kind of relativistic corrections into account, if you just observe that. But time dilation kind of induces a novel effect conceptually, which is this entanglement. So you have now entanglement of different degrees of freedom, which otherwise would not correlate in any way. And so this is kind of a signature of underlying geometry of space-time, in fact, bending of time, in some sense. Okay. All right, but so yeah, the experiment is still challenging, but it's not so far away. So I think, just to briefly mention, like I said, this isn't a universal effect in the sense of it doesn't matter if you do use atomic fountains or spins or any type of system, and it has to do just universality in the sense as that time dilation is universal. It affects any system in the same way because you're not actually changing the Hamiltonian of the system; you're changing just the proper time in the same way. So you can use a periodic clock. This is what I discuss here, and the effect on the visibility is the difference in terms of how much time dilation you accumulate on these two paths as compared to the frequency of the clock, basically. You can also do complete mixture of clocks, so not something that we usually consider as clocks, but you can use thermal states. You can use some completely incoherent mixtures of systems which just have some kind of internal dynamics. So you never really have to actually read out the systems either. So then you get kind of a more rich phenomena and effects that take place depending on what energy levels you're populating and how many modes you have inside your system. And actually you can also play a trick and do the same thing on photonic experiments. So it's a little tricky because photons do not actually measure proper time per se. So by definition, there are null curves, meaning that proper time is 0 by definition. So you can't measure time with them if you sit on them, but you can look at their distance, effective distance that they're traveling, very similarly to gravitational wave detection. So there is an effect very related to time dilation, which is the Shapiro delay. So if photons travel through a space-time which is curved, then they effectively are slowed down from an outside observer. So you can use that kind of as an effective clock, just basically a timing experiment, how long a photon takes at a time. So you can do an experiment with just single photon interferometry. And just in terms of numbers, if it's a two-level system, say if you have atoms and you use optical states, it depends on the frequency and it depends on the proper time difference that you're accumulating. So in other words, you need as high frequency as possible of your internal states, and you need as high superposition state as you can get. So for atoms, I think they're the closest to observing it. So it's about 2 orders of magnitude away. So basically, you need a 10-meter fountain in superposition. Keep it at 1 second. If you do that, you will see this effect, which would be a first demonstration of quantum mechanics on curved spacetime, effectively. So it's a regime of physics that we never probed. Okay, and then with photons, maybe it's possible too, but yeah, you need gigantic interferometers. So yeah, maybe. Yeah. Okay, and then in terms of experiments, there have been actually some results in recent years. So the first result was that people just simulated the effect. So simulating means that you have some kind of matter wave interferometer, and then you simulate a different effective ticking rate of your 2 clocks. So it's like, 2 people having 2 different clocks, and they tick at different rates. I have a Swiss clock, and somebody has, an Italian clock, say, and then, it looks like time dilation. So this is the same thing. So you slow down a clock on purpose. So this is here particularly like spin precession. You use an inhomogeneous magnetic field such that it precesses at a different rate. And so you can, observe exactly this type of effect and this beating of the visibility. Then there's a few ideas and actually proposals for space missions that I wasn't involved with, but also ground-based experiments trying to do that with photonic experiments. And then, yeah, of course, for me, very exciting is like the development in atomic fountains. So if really there is kind of a MAGIS 100 detector which is built, they precisely plan to have a superposition of 10 meters. So that's interesting. But then, of course, on top of that, you have to make sure that the proper time difference is actually what enters. So in a usual Kasevich-2 experiment, the proper time difference is to lowest order 0. And so it's also always better to kind of hold them. And this is also some development that just very recently came out from Holger Müller's lab, where there's a superposition experiment only on micrometer scales, but where the superposition is held at 2 different heights for 20 seconds. So that's exactly this type of setup that you need to probe this effect. Okay, right. And then how do you have? Oh, 5 minutes even. Oh, okay. Well, so then finally, this is again a bit conceptual, but it's not as crazy as spaceships in superposition. But this is just pushing this idea further in terms of its universality. So like I said, the effect is interesting for experiments if you talk about controlled clocks. But any system has some kind of internal dynamics, even if you can't really access it. But the point is that this effect does access it, even if you don't want to. So, for example, if you take some kind of large system, so it has a lot of internal degrees of freedom, like a molecule, and you have no control of the internal states. So they do some kind of vibrations, and they could even be thermally excited. Then, in principle, what happens is that all these thermal oscillations start acting as an effective bath for your system, because time dilation couples any oscillation to the center of mass of the system. So, in particular, you can model this kind of coupling. Now, this is just writing proper time in terms of an effective Hamiltonian. So you just translate it to coordinate time and then define a Hamiltonian on that. And in terms of quantum optics, it just looks like an interaction Hamiltonian. So it's very easy to work with, and it interacts, with this is kind of the special relativistic time dilation. This is V over C squared effect, and this is the general relativistic time dilation. So this is phi over C squared, the redshift effect. And what it just tells you is that your center of mass degrees of freedom couple to any kind of internal Hamiltonian that your system might have. So let's say just as a simple model, nothing depends on this model, but just as a simple model to take n-harmonic oscillators which are inside your system, if you take that and then you try to create a superposition state of your entire center of mass of the system, and you just say it's a thermal state, and it doesn't emit anything, it doesn't interact with anything. Now, the only thing that happens is because you're in a gravitational field, these thermal oscillations will feel a different redshift. So in other words, even thermal oscillations are slowed down in a gravitational field. So effectively, temperature is actually lower, closer to Earth than it's higher away. And this effect alone is enough to decohere your system. So you can just do the math here. Basically, you just integrate out all the internal degrees of freedom of your system, but because of this interaction Hamiltonian, you get a decay of your coherence, which goes as a Gaussian decay. And it scales with the number of particles, so the size of your system, and basically the temperature of your system. So it's kind of a cute quantum mechanical, gravitational, and thermodynamic effect which kicks in. The numbers are not so good, so it's interesting conceptually. So if you have some kind of micrometer scale object at room temperature and you create a millimeter size superposition, then you get some kind of also a millisecond effect or microsecond effect. But it's of course not something that's readily available in the lab. But as a conceptual thing, it's quite interesting. It's kind of the other limit that even without any external environment, in an entirely empty universe, you actually get loss of coherence in your spatial degrees of freedom from the fact alone that your particle is composed of other particles. So it decoheres itself in some sense. But it's fully within quantum theory, so there's nothing speculative about it. It's all fully unitary. It's just that you couple to a different Hilbert space. Okay. And then I think I'll skip it. It's just some ideas for experiments that you might be able to do, which could be interesting, using nuclear states and then use an entangled state and so forth. But I think I ran out of time anyway. I mean, I'm happy to talk to you about it over a coffee break. So this is the summary of, I don't know, something like 7 different projects that I try to squeeze in here. But the basic idea is, I think it goes both ways. There's interesting ideas theoretically which are inspired by what people are doing in the lab and just quantum effects we can observe, like these Bloch oscillations. Also ideas from just quantum information theory to learn something about high energy physics or even quantum gravity can be applied. But then also reversely, actually, there's new ideas at low energies for new experiments and new kind of possibilities to test fundamental physics, which go beyond just simply speculative models where somebody postulates, some kind of, I don't know, dark matter particle or something, which is just has something to do with, just pushing physics to new regimes where we have never probed it, and there's actually new effects that appear. Okay, and so with that, let me thank also collaborators that were relevant for these projects, and thanks for your attention.
Thanks so much, Igor. Do we have questions?
Remember that you can always take an Newtonian limit and still talk about time dilation. So I wonder, how do you know if it's like GR time dilation or is it phase shift because of some force? I mean, you have to be strong enough, I don't know, fields or?
No, so you need very weak fields. So here, it depends a little bit on the semantics of Newtonian limit. So, I mean, Newtonian limit per se does not have the redshift. But you don't need full-fledged GR to explain, let's say, this effect. So this effect alone is like 1909 effect. It's not 1915 effect. In a sense, it's the first test of GR, but you don't need Einstein's equations for that. It's enough to kind of use special relativistic E equals mc squared and relate it to the gravitational mass of a system. So that's enough to explain the first order redshift. So it's kind of Newton plus special relativity gives you this effect. But of course, this is already GR. I mean, it's kind of, that's, first step or whatever it is. But so it's a 1/c² correction, which is beyond special relativity due to just velocities. And you can have, of course, just normal acceleration that can kick in. So that's exactly right. But in terms of, just Newtonian physics, you don't have, your time has to change. So what you're looking, no matter what you call it, what you're looking at is, effect which slows down your particle. And in fact, you can do it in just pure SR just by velocities or acceleration.
Can you think of a potential that changes the energy?
Yes. Sure. You can construct a potential, like I said, like for example, inhomogeneous B field, if it couples to spin precession, would give you a similar thing. It will give you a different precession at different places. But that is, the main difference is very specific. So if you happen to have like a spin, and if you happen to have this homogeneous B field, you'll get a similar effect. This is the simulation part, or analogous part. If you now put in a different type of clock, which is, I don't know, some kind of oscillator, doesn't couple to the B field, it will behave differently. So kind of the GR aspect is always that, it's time itself which is changing. So it's the same, like you can have a redshift without GR, but, it's still an effect, it's still a test of GR if you make sure, you don't have any kind of other field that happens.
Just directly following up, can you go to the next slide then?
Yeah.
Because there's a statement that contrasts now. No, next.
Yeah.
Sorry, yes, exactly.
Yeah.
here. So what you just said was basically the left side, right? The yellow. You just explained that the phase shift actually basically you don't need the notion of redshift. But somehow if you go to the red part, you say there's a difference, there's a fundamental difference.
Yeah.
Namely?
Well, so to explain that you have entanglement here in the context of, say, gravity and in this universal... So let me put it this way. You can get entanglement without gravity in quantum physics. That's for sure true. Okay, so there's nothing special about getting entanglement. The point is that what GR does on top of Newtonian physics is it induces this type of entanglement, which you don't get in a kind of, in a non-metric theory, effectively, or in a theory which has only Newtonian physics in it. So once you get this kind of entangled state, and let's say you verify that, it scales, with all this GR parameters, and it's not just simply some stray magnetic field that happened to couple to your system, then, then this you can only explain if you include already, some kind of, G00. Basically, your G00 component has to be not 1, but it has to have, additional factors in it. And so that you can only explain, in this way. Only in the sense of, within the GR framework. Yeah. Whereas, if you just look at the phase shift alone, even if you look at GR corrections, in principle, you look at kind of the force limit of that in some sense. So, this is just to say you can look at conceptually different type of effects if you look at different observables.
So I think it's all really sort of exciting stuff, but I guess my question is from a conceptual perspective, what you're doing is actually taking exactly what we kind of expect from quantum mechanics and exactly what we know from GR.
Exactly.
So say you do all these experiments, what have you learned about how quantum mechanics and GR actually interact with each other, or how to unify them, or have you learned anything?
Well, you do learn something. You don't learn how to unify them. So this is what I meant before. Like these type of so now you're talking about just quantum theory, let's say on curved spacetime with a fixed background. You don't learn about a quantization of gravity unless you have, again, you can always cook up some model that you rule out or something like that. So that's not the motivation. The motivation is just to push, physics that we haven't tested yet in a regime where it hasn't been. You learn about, that you can include effectively in the dynamics also GR corrections. So you do kind of quantum theory on curved spacetime just as Hawking radiation in a high energy limit. But it's something that we can derive. So it's not something that is speculatively put on top of something, but it's something we derive. So it's a good, to push it and test it. And then on top of that, I think you can always, probably, cook up. So I'm sure, for example, so the theory that Jake talked about before, where you have some kind of, that gravity speculatively as a force which does not allow entanglement as an interaction. So here it's a bit different. We're talking about time dilation, not even about force and so forth. But again, most likely, I think it would exclude certain effects that I see here. Actually, I don't know. That would actually be an interesting project. I can put a, if you send me some PhD student, he or she can look at it. But, I think in that context, one can probably touch base with a lot of these models, but that's not as much kind of the initial motivation. It's more to push, physics in a regime where, we have absolutely zero experimental input.
Okay, Tsugato, and then we push the discussions into the coffee break.
So the G00 is kind of a relative acceleration, right? If you define
Yeah.
acceleration. So can you artificially do this thing by giving different, relative acceleration between the superposition and still get your decoherence?
Yeah, absolutely. So you can, here even, so this effect happens already in the limit where you just have homogeneous gravitational field. In other words, by equivalence principle, it's exactly the same as acceleration. So you can put this whole thing in a rocket, you'll do the same thing. So that's exactly right. So, accelerations will be good, or velocities, yes, rotation, maybe some kind of velocity profiles. So that's absolutely right. Yeah.
The reason I say that you have this temperature dependence, right? So
Yep.
if you heat up the system, you can increase your effect.
Yeah.
But then, of course, other things like black body
Exactly.
increase, but you can decrease the separation and give a large.
Yeah, so that's what we looked at. I took the slide out, but but exactly right. We compared to black body emission, and in different regimes in the paper. It's just even to see if you even can have conceptually any kind of parameter corner where you're not masked by black body emission. Yeah, so it's actually better to go down to about 1 Kelvin, because otherwise you're really like kind of masked by scattering from black body radiation. So it's a trade-off, and for any specific experiment, you have to think harder. So it's not a good idea actually for experimental evidence to use temperature. It's better to kind of, do your distributions by hand.
Okay.
I can do them quick.
Yeah, so suggestion, since several people have to leave also at some point, and we are already fully into discussions, we shorten the coffee break by 15 minutes, so that we can continue then a little bit more early and finish more early. Is that okay with everyone? Which means, I think David is the next. Yes. David, 15 minutes, or do you need half an hour?
Yeah.
No? Okay, very good. Okay, so thanks, Igor.
Thanks.
Again, all the speakers.